electrical power. What we're going to have to do is take our original Physics 11 definition of power and tweak it a little bit. So recall, as charges flow through a circuit device, like a resistor, or light bulb, or stove, or whatever, they lose energy due to collisions with atoms in the wire. We said that you start out with a higher voltage, maybe 8 volts, and if the voltage right here is 2 volts, how much voltage did you lose going through the resistor? 6 volts. Technically, you could call that negative 6 volts, but we understand you're always losing energy going through a resistor, so we've long ago dropped the negative. We just say it's a voltage loss or a voltage drop, a drop in voltage. You dropped by 6 volts going through that circuit, going through that resistor. This energy lost by the charges is transformed into heat energy. And the energy lost by charges is related to voltage drop because, remember, we defined for your test next class voltage as potential energy per coulomb, so we could get potential energy by itself, Jordan. We could times the Q over. Potential energy is QV. That's going to be on your test, certainly on Thursday, showing up fairly often. Because this gives us an expression for electric energy, we should be able to now get an expression for electric power, because power was work energy over time. So power, it says fill in the steps below. Power is energy loss over time, and the energy loss is right? And then I wrote grouping. What I really mean is I want you to look at Q over T times V. This is what I want to group. What was charge divided by time? I'll give you a hint. It was part of last day's lesson. It's also on your formula sheet. It's current. It's also in brackets on the next line. It turns out electric power is given by current times voltage. Although I think on your formula sheet it's VI, not IV. Can someone look? Jordan, you have your formula sheet in front of you? Yeah, VI. Okay, fair enough. But there's the derivation. What would the units be? I guess amp volts is another way to write watts, because that is power, and power is measured in watts. I guess, and by now, Kayvon, you've noticed often units can be written in many, many different ways. Well, watts, okay? So power is energy drop per coulomb of charge times coulombs of charge per second. Remember, we said that volts was joules per coulomb, and we said that amps was coulombs per second, because it's charge divided by time. Is amp volts the same as watts? Hey, I get joules per second, I get energy over time. It is watts. Wouldn't have thought of that at first, but there you go. So the units do work. Woohoo! By the way, did I say that later on? Sure. So the rate at which electrical energy is transformed to heat energy, how fast you use up this electrical energy, how much power you use, is given by VI. I'll be honest, now that's the only one on your formula sheet. I hardly ever use that one. You see, what was the first equation that we learned yesterday? Ohm's law. Sorry, I guess it was the second equation. What was that one? The one that has V and I and R in it? Okay. Well, if V equals I times R, I can plug that in for V, and I can get IRI, or wait a minute, what's I times I? What's an easier way to write I times? This one's not on your formula sheet, but it's really easy to derive. I think that's the one that I use the most, just for some reason, it seems in most circuits, when I'm trying to figure out how much power I'm losing in a resistor, like a stove or a kettle or a blow dryer or my iPod, I know the resistance and I know the current. I might not know the voltage source, but I know that, or the voltage drop, but I know that. Well, I also equals V over R if I get the I by itself in Ohm's law. So I guess power equals V times I, V times V over R. Another expression for power is V squared over R. So the one in the box, Jordan, is the one that appears on your sheet. The one that I've outlined in red is the one that I use the most. In fact, I kind of ended up memorizing it. But it's a pretty easy derivation. That third one, the V squared over R, it's fine. Sanj, I just almost never use it because rarely do I know only the voltage and the resistor. Usually I know more than that, just for what it's worth. We call this, by the way, Joule's law. Joule's law is power equals VI. So Joule not only has a unit named after him in terms of energy, he's also got a law named after him. He did a lot of work with electricity, in particular with electrical energy and trying to quantify it. Tough audience. By the way, little technical comment. Really, to find the energy lost, I should use the work energy theorem. I should use work as change in potential plus change in kinetic. But since we've said that all the charges inside the circuit are being forced to travel at the same speed when they're in the circuit, what's the change in kinetic? If they're all being forced to travel at the same speed, what's their change in kinetic energy? Zero. Nothing. So, you know what? I can just go with that one, QV. Okay? Technical point. So, now we can start to talk about how much current appliances draw. Example 3. Find the current in your house wires if you plug in a 1400 watt hair dryer. Okay? The two big equations that we have, the ones that you're going to be flogging over and over, are Ohm's law and Joule's law. Grand total, how many variables do you see in these two equations? 4. The rule is, in any circuit, if you know 2, you know 4. If I tell you any 2 of those, you can, using those 2 equations, find all 4. Okay? If I know 2, I know 4. Last day, I actually said to you, if I know 2, I know 3. That was Ohm's law. It's actually even more powerful than that. You give me 2, I can find 4, which doesn't usually happen. Usually, we needed 3 things to find the 4th in most of our physics stuff.
P&R.
Pardon me?
What happens if you get P&R?
What happens if you get power and resistance?
Yeah.
Patience, young grasshopper. Let's find out. To find the current in your... The answer is, remember, I gave you these 2. That's when I fall back on that one, because if I know P and R, I can find current, and now that I have current, I times R, and I'm good enough to go for voltage, right? They're all there. You just have to sometimes do the substitution. Find the current in your house if you plug in a 1400 watt hair dryer. Okay. I'm going to defic. Power is 1400 watts. The voltage that's running through this hair dryer is 120 volts. Now, it's alternating current, but I said to you last day, most of the rules for for direct current will also apply for alternating current, so this will work. What do they want me to find? Current. Okay. Which equation am I going to use? I can use Joule's law. In fact, I can get the current by itself. If power equals V times R, what's current? Yep. Turns out another unit for amps is watts per volt. Okay. 1400 watts, that's what's stamped on the, and by the way, on almost any electrical appliance, flip it over, it'll have how many watts it draws on the bottom, so you can actually find this data. Oh, and I know that my household plugs give me 120 volts, so if you want to find out how much current, if you're a nerd, you want to know how much current any of your appliances draw, take the power rating, divide it by 120. What do we get here? How many amps?
11.6.
Sorry?
11.6.
So let's go 11.7 amps. Most household circuits can handle 15 amps. Could your household circuit handle this? Yeah. Could it handle 2 blow dryers at the same time? Probably not, depending on how you wired them together, but certainly in series, that would blow your breaker. By the way, what's the resistance inside this particular blow dryer? Probably fairly high, because probably there's an element that glows red hot inside the blow dryer. That's an easy way for us to generate the heat. What's the overall resistance? You know what? I'm going to go V over I, 120 divided by 11.7. Use the 11.6 repeating. What's the resistance in ohms that you get?
10.3 ohms.
10.3? Okay. Now that's the total resistance of that blow dryer. That combines both the resistance of the motor, the fan motor that runs, and I suspect most of the resistance is in the heating element. For you to get a nice hot element, you want a high resistance that has lots of electric friction that's going to generate heat. Very simple. Oh, in real life, most blow dryers have a low and a high setting, or even a low and a medium and a high setting. I bet you all you're doing is you're changing the resistor, not of the heating element, but of how much current goes into the motor, the fan speed. Oh yeah, because when you flip it, it goes from at low running really quiet to high running loud. You're changing the fan speed circuit. It's worth knowing what draws lots of power and what doesn't. If you want to know what draws lots of power, what you really want to do is think biggest heat exchange. What generates the most heat? So on the left, I've got a number of electrical appliances. On the right, I have a number of wattages. They're not in the correct order. Look at the appliances. Which one of these do you think requires or generates the most heat, has the highest wattage? And I'll give you a hint. It's one of 2 appliances that have a special plug. Dryer. Okay. By the way, what are the 2 appliances that have a special plug in your house? Okay, stove, oven, and dryer. They require actually 240 volts. Okay, that if you ever pull it off, you'll see it's got a funky looking plug. That's a special wired 240 volt plug. Handles way more current, and it's limited to those 2. Why? Because they require the most wattage. Why? Because they move the most heat around. What's the highest wattage on the right-hand side? You know what? Clothes dryer. Moral of the story is, hey, don't run your dryer unnecessarily. It draws a lot of power. What do you think moves the next largest amount of heat?
Probably a
Hot water heater. But it doesn't require a special plug. And by the way, yours may not be electric. Many hot water heaters actually run off natural gas now, too. Okay. What do you think moves the next largest amount of heat? Microwave. Small microwaves are usually around 800 watts. Large those are the small little, you know, the ones that you get for college or whatever. Larger microwaves usually are 1,200 watts or even 1,400. That's why whenever you're looking at a microwave recipe, in the instructions for cooking time, what does it almost always say in brackets? Cooking times may vary. Why? Because they don't know the wattage of your microwave. They don't know how much power your microwave can put into the food. So what's the next biggest? 1,200? All right. You know what? I know the wattage of a light bulb. What's an average light bulb? I've put light bulbs in it, and so I've read on the end. You know what? Light bulb is 60 watts. I can do that. We have computer, clock, and kitchen fan. Which of those do you think uses the most power? Computer. They generate actually a fair bit of heat. Okay. Most of your computers have a fan that runs to cool it off. So 800 watts for a computer. Or a heat. Yeah, there's all sorts of options as well. Yep. Of the two that are remaining, which one, A, generates very little heat, and B, can run off of a small battery for a very, very, very long time? Clock. Draws very little power. Clock uses about 0.1 watts. It's a very efficient system. Oh, and I guess a kitchen fan, about 150 watts. Okay. On the old Physics 12 provincial, a classic multiple choice question is they would give you 4 appliances and they would say, circle the appliance that would likely have the highest wattage or the lowest wattage. And all you were saying is, well, which one of these moves the most heat or the least heat? Gives you an idea of what's really big and really small. Sorry?
So I'm curious, why does a dryer have a higher power draw than a hot water heater?
Hot water heater heats up the water slowly. It doesn't move the heat very, very fast. Okay. That dryer's got to put a lot of heat in there, and it's fighting, right? Understand, that soggy clothing does not want to dry very quickly. It's holding a lot more water than you realize. And you might say, well, Mr. Dueck, a hot water heater. But the other thing is, once the hot water heater is full, right, you're almost never draining the hot water heater and refilling it with cold water from scratch. It just trickles. That's why it takes several hours for a hot water heater to reheat. Okay?
Okay.
Yeah.
I was just like, because like,
yep.
It must hold like a couple hundred liters.
Yeah, but we don't heat it very fast.
No.
Yeah. It's designed to be basically a trickle heater, essentially, right?
That's why it gets cold and get like,
yeah.
Family, you get also showers at the same time.
Yep. Now, some natural gas systems can heat up almost as fast as it drains, not quite, but they can last longer. You'll see in the commercials, and you'll have almost indefinite hot water. What they really mean is, you know what, if you drain this, let's say, we can replace it at about 80% of the rate that you drain it. So it's going to run out eventually, but it's a lot better than a trickle electric heater. Electrical energy. Since power is energy over time, we can solve for energy, and we can find, I guess, energy is going to be power times time. Right? Specifically, electrical energy, electrical power times time. The unit for this would be the watt second, which is really small. By the way, the unit for that is also a joule, but a joule is also a watt second. It's really, really small, but I want you to notice the unit is power times time. On your bills, you guys don't get them yet, but most you'll be moving out in the next few years. The bills that you get from BC Hydro will be measured in kilowatt hours. Can you also see kilowatt power times hour time? Because a kilowatt hour is a much larger measurement unit. It makes it easier to do the math, okay? So since a joule is a relatively small unit of electrical energy, it's common to use a larger unit, the kilowatt hour, where 1 kilowatt hour, well, kilo means 1,000 watts, and 1 hour is 3,600 seconds, so 1 kilowatt hour is 3.6 times 10 to the 6th joules. Typical household uses between 1,000 and 3,000 kilowatt hours a month. And you can imagine if we did that in joules, you'd be getting a bill that would have numbers in the trillions, and most people just can't wrap their brain around that if it was in joules. But kilowatt hours, yeah, between 1,000 and 3,000, okay. So, if a 60-watt bulb is left on all month, let's say a 30-day month, because months have different lengths, 24 hours per day, how much energy will it use in joules? Okay. Well, power is work over time, so work or energy is going to be power times time. How much power does this bulb draw? Read the question. How much power does this 60-watt bulb draw? How much power does this 60-watt bulb draw? Huh? 60 watts. How long are we going to leave it on for? Well, 30 days, but now I need to do a conversion. I want days on the bottom, hours. How many hours in one day? 24. Remember doing this in Physics 11. Now that gets us into hours. I want hours to cancel seconds. We did this a couple of days ago. How many seconds in 1 hour? 3,600. And let me double check. I think days cancels, hours cancels, and we are left with watts and seconds, so the units are good for joules. Okay. How many joules of, not power, Mr. Dueck. How many joules of energy, if you leave a light bulb, a 60-watt bulb on, for an entire month, how many joules of energy will it use? 60 times 30 times 24 times 3,600. I get that, don't I? Yes? 60 times 30 times 24 times 3,600? Or no? Yes? Yeah. 1.5 times 10, 1, 2, 3, 4, 5, 6, 7, 8. 1.56 times 10 to the 8th joules. That's one light bulb. You can imagine if we reported energy bills in joules for your entire house usage, the numbers would be huge. They'd be having so many zeros. Most people without a good math background their eyes would swim. Or they could report it in scientific notation. How many of your parents know how to use scientific notation? So we change the units. Go to kilowatt hours. You got it okay? Yeah? Okay. I'm guessing you probably forgot the 60 in front. Yeah, I figured so. I know my audience. B says, repeat in kilowatt hours. Okay. If I want to change this to kilowatt hours, it's 1.56 times 10 to the 8th joules. And the conversion factor I have is 1 kilowatt hour is the same as, what did I have slightly up there in the box? 3.6 times 10 to the 6th joules. There's my conversion factor. Joules cancels. Now, on your test and on your quiz, on your test for sure, I won't give you anything in kilowatt hours. I won't make you do the conversion. In your homework here, because when you get your bills someday, they will be in kilowatt hours. In your homework, I will give you some questions on that, because you should know. It's just, you probably noticed I have a bit of a, I don't like making you do unit conversions on a test. I figure I tested that last year in Physics 11. This divided by 3.6. Oh, there. That's a much nicer number. That your parents, that you guys, that the average adult can wrap their brain around. Oh, if I leave this light bulb on, I'll use 43.2 kilowatt hours. Part C. Given that BC Hydro charges about 6 cents per kilowatt hour, now that's knowing my audience. Come on, gotta be a little impressed here, huh? Find the cost. By the way, I have to check. I don't know what BC Hydro charges now. It may not be 6 cents. Google, because I wrote this about 8 years ago, and I know prices have gone up fairly dramatically, right? Currently, right now, the government, what they've done is they've lowered taxes, but they've raised rates everywhere because they got to get their money from somewhere, but you'll always be popular if you lower taxes, and most people don't look at their bills very closely, right? Let's see. I have 43.2 kilowatt hours times 0.06 cents, I'll make it dollars, per kilowatt hour. By the way, do you notice how I figured out why I wanted to multiply? Because when they said per kilowatt hour, that meant it was on the bottom of that fraction, and it's on the top of my original. I can get kilowatt hours to cancel. And this is a problem, Cole. We live in a situation here in BC where energy is so cheap that there are people who'll say, oh, it's only going to cost me $2.60 to leave a light bulb on all the time. I'll leave it on all the time. Of course, that's one bulb. They add up. Really, we're not doing energy savings for the math, for the money. We're doing energy savings. The reason we preach energy savings is for the environment, because Well, what do you guys think? In the future, do you think we're going to be wanting to use more electricity or less electricity than right now? You guys have noticed we are becoming an electric culture. What we don't want to do is to have to build more hydroelectric dams. We built them in the 1920s, 1930s, 1940s. If you're looking for a good day trip, the Stave Lake Power Center, which is just down Dewdney Trunk Road, is a spectacular day trip. We did not know that they would do so much damage to the salmon runs, to the salmon fishing, to the rivers. Once they're built, they're basically a green source of energy. It's just that building them damages the environment substantially. So what we're trying to do is make all the ones that we built more efficient and continue to use it. We're trying to avoid building more if we can avoid it at all, because our salmon industry has already been pretty devastated by overfishing, but also by, hey, we blocked a lot of the major rivers that salmon's used to spawn in. Whoops. Didn't know. Sorry?
Also, the guy that built the pump back 20 years old, $3 billion to a giant project like a dam.
Yeah. Well, it creates jobs, right? Certain things always go over in terms of popular.
It creates jobs, so they
Yeah.
have to extend it still. Let a
Yeah.
private company build it.
Now, that's pretty cheap. And we do have access to fairly cheap power. Some countries don't, right? Certainly there are countries where electricity is way more expensive. Even the U.S., you guys don't remember, but about eight years ago, California had a massive energy shortage in the summertime. Air conditioners. They actually had to have rolling blackouts. So you were told from 8 p.m. to 9 p.m., your town won't have any power for that hour on Tuesday. And you knew it was coming up, and it just literally rolled all the way across the state. That was how they saved power. We sold them a whole bunch at a pretty inflated markup because we had extra.
Don't we still do that with the
I don't know, because our power usage has gone up, and I know that our power creation ability has not gone up at the same rate as usage. But I know we used to have extra. I haven't done the research or done the Googling to see what we're doing lately. It's a good point. I need to. In fact, I need to find the price per kilowatt hour.
Also, they built a whole bunch of dams in that huge sound like
Yeah. Well, the big one was the on the Columbia River. That was built in the 1930s, I think. But it, at the time, was the largest dam on the planet. Also, though, did some, changed the entire, created a huge man-made lake behind the dam, which changed all that environment and all. We didn't know at the time. Efficiency. Recall, efficiency was power out divided by power in, or work out divided by work in, or energy out divided by, you know what? Here's what I said. Efficiency, sorry, that's too small for you guys to see this symbol. That thing is always that's not the official equation, but I know in our universe, Tanisha, we can't have more than 100% efficient. So if you are getting more than 100% efficient, I'm sorry, you haven't won the Nobel Prize. You've done the physics wrong. Okay? Oh, and then times 100%, and make sure units match. And what I mean by that, Doug, is don't divide joules by watts. That's the big one. Make sure they're either both in watts or both in joules. So in the box here, it's E out over E in, or power out divided by power in, work out divided by work in, and then times 100% to make it a lovely percentage. Let's do some physics that our politicians in Ottawa did, but arrived to the wrong, dumb conclusion. Well-meaning conclusion, but the wrong, dumb conclusion. Example 6. A 60-watt light bulb is connected to 120 volts. Okay, so I've got the power, I've got the voltage. Woohoo! It produces 58 joules of heat and light every second. It's left on for 8 hours. Electricity costs 6 cents per kilowatt hour. All right, first of all, the current through the bulb. Well, they told me the power running through the bulb is 60 watts. 58, oh no, that's joules, not watts, careful. The voltage I don't suppose I have an equation that has current, power, and voltage in it. That'd be convenient.
I equals V over R.
No, that has resistance. Thank you for playing. Collect your consolation prize. That has power and voltage in it. Yeah, you're going to have to turn back a page. Joule's law, which was what? It's also on your formula sheet. Power equals VI, right? And V equals I times... These are the two big ones, but power equals VI. So I guess power divided by voltage... Oh, I can do this in my head. Doug, in your head, what's 60 divided by 120? Running through that light bulb is 0.5 amps. I guess technically 0.50, 2 sig figs, right? Okay. B, what's the resistance of the bulb? Let's use Ohm's law, V equals I times R. Let's get the R by itself. R equals, Jordan, my friend, if I get the R by itself here, how would I get the R by itself in Ohm's law? Divide I? It sounds like a British, divide I, say. No, divide me? No, divide I. Oh. Okay. You waking up? 120 divided by 0.5. Hey, I should be able to do that in my head, because dividing by a half, dividing by 0.5, what's that the same as multiplying by? No calculator, Sanj. In your head, 120 divided by 0.5, which is the same as timesing it by 2. What's 120 times 2 in your head, please? Yes, thank you. This bulb has a resistance of 240. Remember, the units for resistance are ohms. By the way, why don't we use that as our symbol for ohms? Yeah, that we don't want to put zeros where they shouldn't be, right? Even the oxygen molecule, we're lucky that it's almost always O2, so that we can tell it's an oxygen molecule and not a zero. Right? C, efficiency of the bulb. Okay. Well, the power in, power out is going to be energy divided by time. How much energy are we getting out from the bulb? What does the question say? In how much time? Keep reading, Doug. No. Keep reading right after the 58 joules. Keep reading. Doug, in your head, what's 58 divided by 1? You had to, that one? Really? I don't think you, okay. So we're getting out 58 watts. Well, no, we're losing, we're producing 58 watts of heat and light every second. Most of that goes into heat, actually. But how efficient is this bulb? Well, efficiency is the smaller number divided by the bigger number. Oh, times 100%. $58 divided by 60 times 100%. You get 96.7% efficient. Now, the only reason it's that high is because I included heat in that calculation. I said it produces 58 joules of heat and light. It turns out most of that energy goes into heat. And so politicians saw that, in fact, if you just only look at light, incandescent bulbs are about 8% efficient. They're about 92% inefficient. Politicians saw that. And they said, oh, okay. I can't remember if I'd done this speech with you guys before about why. Okay. So they said, let's replace all of these inefficient incandescent bulbs with the fluorescent. They're banned now, right? The incandescent ones, as of this year, are no longer, it's all fluorescent. You're supposed to replace all your household lights with the little curly, spirally fluorescent ones. Well, there's a problem. They didn't realize that that heat doesn't vanish. Your heating bill is lowered by exactly the amount of heat that those light bulbs give off. It's not wasted energy. They're inefficient, yeah, except your house indoors captures that inefficiency. Okay, outdoor bulbs are inefficient. Those fluorescent ones don't work really well outdoors.
Why?
They don't deal well with water. They don't like moisture environments. Okay? Have you not noticed? You either have to seal it, which is what the street lights do. Okay? But just the standard ones, no. We still have the floodlights for outdoors. Okay? Well, it could be argued that in the summer, fair enough, light bulbs heat up your home, and you don't want to heat up your home in the summer, so they're inefficient then. True enough. Logan, what country do we live in? Northern Hemisphere?
Yeah.
In the summer, are our days longer or shorter than most of the world? In the summer, do we use light bulbs more or less because the days are longer?
Less.
So, you know what? Really not that big an issue in terms of heating up my home in the summer with light bulbs. This was poorly thought out, especially because, and this is for all of you as science nerds, these fluorescent bulbs, the screw-in ones, you cannot throw them in the garbage. You cannot. Okay, they contain mercury, and when mercury gets in the environment, we have no technology right now for removing it from the environment. It flows into the oceans, it goes into the fish. All of you have way more mercury in your system than 2 generations ago because we've been disposing mercury in the environment and we have no way of getting rid of it, and you've all absorbed it through seafood or through things that ate seafood. Mercury's not good. You have to dispose of them properly. You actually have to take them to a proper recycle disposing place where they clean out the mercury. So we have an environmental hazard for not much savings. Poorly thought out. There's my rant. Oh, what is the future? LED bulbs. Those are just starting to appear now. LEDs have been around for a long time, but just 2 years ago, the Philips light bulb company had a prize. They offered $1 million to anybody who could design a screw into a standard light bulb fixture LED bulb. Normally LEDs are very directional, which is why they make good flashlights. They said, can you make one that's omnidirectional, goes in all directions? Conveniently, Philips won their own $1 million prize, fixed, but you're starting to see them in stores now, but they're like 15 bucks a bulb, 10 bucks a bulb. Once the price drops down, I'll replace all my bulbs with LEDs.
How do they do it?
Pardon me?
How do they do it?
How they do what?
Whole bunch of LEDs?
And some diffusion filters and stuff. Yeah, they're quite clever, and they work quite well, and they use very little power. So my 60-watt incandescent, I think the LED can do the same for 5 watts in terms of brightness. Okay, very, very efficient. Don't give up much heat. So that's the future. D, how much energy did we use? Now, Cole, we're going to look at total energy. We need to take into account the time. So we said power is work or energy over time. So the total energy is going to be power times time. We're using 60 watts. How long is this bulb left on for? 8 hours. I got to do a conversion. So that's going to be 8 hours times, get rid of hours, 3,600. How many joules of energy? Uh, 1.73 times 10 to the 1, 2, 3, 4, 5, 6. Joules of energy. E. What's this going to cost? Is it E? What's it going to cost? Yeah. Well, first I have to convert this joules of energy into kilowatt hours. So I'm going to start out with the 1.73 times 10 to the 6th joules. And then I had that conversion factor for joules for kilowatt hour. 1 kilowatt hour was, what was the conversion factor from the previous page? 3.6 times 10 to the? That's going to give me kilowatt hours, and then I'm going to multiply that by 6 cents per kilowatt hour. Double check my units. I think joules cancels, kilowatt hours cancels, and I'm just left with a dollar sign for money. This is dollars and cents. So it's going to be this times 0.06 divided by 3.6 times 10 to the 6th. Not much. Again, we don't turn lights off for money. We turn lights off for the environment, which to me is priceless. Okay? Right, you end up with 3 cents to leave it on for 8 hours. Now, you know what? Let me pause the video, find out what the cost is currently. So we just checked. The price isn't that much higher than 6 cents. It's about 7.5 cents, although the maximum rate is nice. It basically is double 6 cents, so you could double these values. But even so, we're lucky. Electricity is cheap, which is also one of the reasons why we've bent our technology that way. It's a cheap, fairly easy to create form of energy. Not unlimited, but pretty good. Turn the page. What's your homework? Study for the test. What's your homework for a week from today? You guys do have a 4-day weekend coming up. Number 1. Number 2. 3 is good. 220 watt computer, 110 volts, alternating current left. You know what? You all have computers, you should know. And 220 watts, that's a laptop. That's something fairly small. It's not a major. Well, yeah, and they have gotten better. But remember, really, when you think computer, we should also say a bigger monitor has to have more energy because you have more electrons hitting the screen. Even though it's different technology, it's going to use more energy. So the size of your monitor would affect that. Honestly, what kind of processing you're doing affects that, right? Sleep mode, it uses less. If you're running a lot of numbers, you're using more. Anyways, 1, 2, 3, 5.